Okay, so sample means. So sample means just sample proportions, right? The sampling distribution of X bar. So sample distribution of X bar is kind of like what we did last week with all the numbers, right? If I was to graph all of those numbers on a dot plot, they'd look like this, right? They'd look like that. They would look like this, right? The top one is when they took a sample of 5. The bottom one is when they took a sample of 20. Now, what do you notice about the differences between the graph of sample of 5 and a sample of 20? What's the biggest glaring things that you notice between the two graphs? Less variability in which one? The lower one, right? The lower one. That is because the sample size is bigger, right? The bigger your sample size, the lower the variability. Go hand in hand. Always, always, always. It's called the law of large numbers. The more sample size you get, the less variability, which is good because I really want to know what the true answer is. What is the true answer? The picture is a little more clear from the sample size of 20 versus the sample size of 5, right? That's true. So they were trying to find the true average. They had a bucket of pennies and they took sample size. They reached in there, grabbed all the pennies, and then found the average year they were made, right? So they wanted to know what was the average year for all of the pennies in the bucket. So they took sample sizes of 5, sample sizes of 20. I used to do this, but it's kind of disgusting because you got to reach in and grab pennies, and pennies are the grossest form of money because they're just passed so much. Pennies, everyone has extra pennies, and it's just I don't do it anymore. Just especially after COVID, when when germs and everything. So I used to do that. I have a thing of pennies. I used to have students grab in there. What's the average date? What's the average date of the pennies? So they take a sample of 5 pennies, and then they add up all of the dates, divide by 5. That's how they came up with the top one. And then they take a bigger sample. I didn't do 50, I didn't, or sorry, 20. I did, and then we did 20. So you did, and then when you reached in there, you had a sample of 20. So you had 20 pennies. Add up all 20 pennies dates, the dates they were made, divide by 20, and then you do that. And then we kind of like we did with points, LeBron James and the points. But like I said, I used to do that, but I don't anymore because it's just not as clean as doing those over there. But yeah, for anything you take sample sizes of, you can do that. Okay, and the bigger your sample is, the less the variability. Okay, the less the variability. Um, okay, so if I was to do that infinite number of times, if I was to find an infinite number, so if I was to do this or this, take a sample of 20, take a sample of 5, an infinite number of times, an infinite number of times, and then I was to look at all those x's and find the average of all of those x's, that answer would be the true center. That would be the true center. Okay? We can't do it an infinite number of times, but we can do it as many times as we can. Okay? All right, so here we go. This hopefully box looks familiar. You have for proportions. Now we have one for means. Okay? So mean, also known as, it's a measure of center. The mean is a measure of center. So how do I find the center of the sampling distribution? Exactly like how I said. It's always going to equal whatever the true mean is. Okay? It's always going to equal whatever the true mean is. So like, looks like the center here is somewhere between 2000 and 2005, somewhere around there, right? That's the center. It's the center of this guy too, but this one has variability to it, right? Center somewhere between 2000 and 2005. Well, if I was to find infinite number, if I was to keep doing this, keep reaching in and grabbing 20 samples of 20, or keep reaching in and grabbing samples of 5, eventually, and then I took all this, took the mean of all of those, eventually I would get the true mean, which that says the mean of all the x bars is equal to the true mean, whatever the true center is. Okay? Standard deviation, that's the spread or variability. Okay? We have a formula for that one. So the standard deviation for all the x bars is the standard deviation divided by the square root of x, or sorry, the square root of n. Okay. So, where's my... So your formula sheet from last semester. The front side, we use mainly for first semester. But there are some stuff in here, the bottom right here. This stuff right here. These four things, right? Center, oops, center, center. One's for mean, one's for proportions. Spread, spread. Right? Those are on there so you don't have to memorize them. They are also on the back. Right there. There's for proportions, there's for means. Okay? So, we also have the 10% condition though. We can only use that formula if the 10% condition, or only I shouldn't say we can only use. The formula is only reliable if the 10% condition is satisfied. 10% condition is still the same. I haven't changed that. Okay. Just a little notation from your book. This is straight from your book. I literally cut and pasted this from your book. We've seen a lot of symbols. We've seen a lot of symbols, right? These are some of the symbols we've seen so far, just in this chapter, just in chapters. Some of them we've seen throughout the year. Some of them we've seen in this chapter. We've seen all of them in this chapter, but there are a lot of symbols. So the key thing from now on, you're going to be seeing those symbols quite a bit, okay, is to know what they are, okay, because if you don't use the notation correctly, you can be marked off for that. Okay, you can lose some credit for that. So the key thing is knowing what what are these are. P hat is the proportion of the sample. X bar is the average of the sample. N is the number in the sample. P is the true proportion. Mu is the true average. Lowercase sigma is the true standard deviation. Mu sub p hat is the mean of all of the samples proportions, standard deviation of all of the sample proportions, true average of all the sample proportions, and the standard deviation of all the sample proportions. So there are a lot of symbols. There are a lot of symbols. Now it says they all have specific meanings and different meanings. Either use the notation correctly or don't use it at all. That doesn't mean don't identify things. Like if I have something like 5, that doesn't mean just leave it 5. If you don't remember which notation goes with 5, write it out in words. Like, I can't remember if it's p hat or p. I can't remember what it was. Then actually write it in. Then actually use a sentence and write it in what it means. Don't just say 5, because 5 could be anything. Okay? So when they say don't use them at all, it means the symbols. We use symbols in math, so we don't have to write it out, right? If I want to say the mean, of the population is 5, I'm going to say that. But if I don't know what symbol to use, I actually have to write it out. The mean of the population is 5. You know what I mean? So don't just say, because a lot of times students read that and they're like, oh, I could just put 5. No, it means don't use the symbol if you don't know what it means. So if you're trying to say something and you don't know which symbol to use, say it in words. Okay, just don't leave naked numbers. okay? Because 5 could be anything. You don't know what, okay? I would suggest we're going to be seeing these symbols a lot. Get to know the symbols, okay? Because, like I said, you're going to be seeing them a lot. We've already seen them this chapter. Next chapter, we're going to be seeing the same symbols. The only symbols that we really don't see from now on after chapter 7 are these guys here. This is really just those really you'll see in chapter 7. The rest of them you're going to be seeing the rest of the year. Chapter 8, chapter 9, chapter 10, chapter 11, so on and so forth. Okay? The ones I circled, those are the ones that are really mainly chapter 7 formulas. Okay? Okay, so example number 1. The question's different, but A and B are going to sound very familiar. Very familiar. You're going to be like, haven't we done this before? We've done something close to it. We just haven't done exactly this. So the question, number 1, the number of movies viewed in the last year by students at a large high school has a mean of 19.3 movies with a standard deviation of 15.8. Okay. Suppose we take a simple random sample of 100 students from this school, and then calculate the mean number of movies viewed by the sample. Answer the 2 questions. Okay, so mean of 19.3 movies. What is that? I know it's a mean, but what type of mean? Is that a population mean or is it a sample mean? 19.3 movies. It's from the whole entire school, right? So population mean. So since it's a population mean, we're going to give it the mu, the lowercase mu, 19.3. Same thing with standard deviation. Standard deviation is a population, so it's 15.8. Okay. N is 100. Okay. Identify the mean of the sampling distribution of X bars. So they take sample sizes of 100. Somehow they take a sample of 100. Large school, so thousands of students. They take samples of 100. Ask each one of those 100 people, how many movies did you see last year? Okay, then write down all 100, what all 100 people say. Find the average of that. Graph it. Put a little X word in. Okay? If they were to do that an infinite number of times, what would the true center be? The same as the population, 19.3. So we would say that the mean of all of those samples would be the same as the true mean, which is 19.3 movies. If you did it an infinite number of times, that's what you would get. The same as the population. Okay. Same thing with proportions. Nope, they're asking for the mean of the sampling distribution. That was letter A. Okay. B, calculate and interpret the standard deviation of the sampling distribution of X bar. We just talked about that. It's the formula, right? One in the dead center. That tells me about spread of the sampling distribution. Okay. A lot of times students say, oh, standard deviation, 15.8. No, that's for the entire population. They just want to know for the samples of 100. Okay. So we have the standard deviation of all the X bars is the population standard deviation divided by the square root of n. So 15.8 divided by the square root of 100, which is 10. And you get 1.58. So the population standard deviation versus the sample standard deviation. Which one is bigger, the population or the sample? The population is bigger, right? It's 15.8 versus 1.58. Why is the sample standard deviation smaller? It's always going to be smaller. For the most part, it'll be smaller. Why is it smaller? There's less variability. Why, though? So the sample is based off 100 people, right? I take 100 people, I find out their average movies they saw. Population is only based off of one. If I was to pick a random person, just one random person, that's based off of that. The sample is based off 100. So it's 1 versus 100. So obviously, the bigger the sample, the smaller the standard deviation. So the bigger my sample is, if I had a sample of 1,000, that would even go even smaller and smaller and smaller and smaller. Because the question they'll ask is, how can standard deviation get smaller? What are ways we can make standard population, or what are ways we can make standard deviation of the sample smaller? Make the sample size bigger. Make the sample size bigger. Okay. Interpret. Well, on average, the sample mean is 19.3 movies. It will vary by 1.58 movies, or something like that. You don't have to have exactly, but just you don't have to have word for word exactly what I have, but something along those lines. Something along those lines. As long as you read it back to you and it makes sense, and it says essentially the same thing, that's fine. Okay? It's just standard deviation. It's just interpreting standard deviation. When you're interpreting standard deviation, mention the mean, and then mention something about a vary, or something like that, because that's what standard deviation is. How much do every sample I take won't have an average of 19.3. Just like every number there isn't 27.5. But they're going to vary by how much. That's what it means there. And then we got to verify 10% condition now. Yep, that's what we have to do. We still have to do that. Okay, so verify a 10% condition. 10% condition for means is exactly the same as a 10% condition for proportions. We have to see that n is less than or equal to 10% of big N. N is 100, less than or equal to 10% of big N. If you have a number, throw it in there. If you don't have a number, just explain who the population is. Okay? So little n is the sample of 100. Big N, where did that sample come from? Where did the sample of 100 come from? A population of large high school, right? A population of from a large high school students, right? So I don't have that number, so I just put the population. So I say students at a large high school. We don't know what that means. Large high school could mean different things. I mean, there are high schools in Texas who have almost 10,000 kids. They're huge. For this area, large high school is probably over 2,000, right? A large high school is probably over 2,000. So East Campus would be, they're about 2,000. Garza's not there yet. So that's just, it means different everywhere else. Yeah. Okay. All right. Okay, so next thing. Conditions, the rest of the conditions. The first two conditions are exactly the same as proportions. SRS, 10% condition. Good there. The last one, the third one is the one that changes for means and proportions. Okay? So it's on the next page. It's not n times p is greater than or equal to 10, or n times 1 minus p is greater than or equal to 10. We can't use that one for means because there is no p. What does p mean? P means proportion, doesn't mean a mean. So we have to use something different. So we have a couple different options. The first option is the shape normal? If they state, sometimes they'll state the population size is normally distributed. If that's the case, we're good. We just say the population, so any sample that I take from it is also going to be normal. Okay? The most common one you'll see is the second one. It doesn't state, nowhere does it say it's normally distributed, but my sample size is big enough. My sample size is big enough that I can assume the shape is going to be approximately normal due to something called the CLT. CLT is the central limit theorem. Central limit theorem. Only works with means. Central limit theorem only for means, not proportions. Proportions has their own set of rules, which we talked about last week, Thursday and Friday. Proportions has their own set of rules, so don't mix them up. Means. So what the central limit theorem says is when the sample size is big enough, we can assume that the shape is going to be approximately normal, even when the population is not. How big is large enough? About 30, around 30. So if a population is, if a sample size is around 30 or higher, we can always use that one. Okay? There will be some times, rarely though, when your sample size isn't big enough, below 30. And they didn't say that population is normally distributed. Hey, calculators? They just gave you some? Yeah. Thanks. Then we have to check for outliers and skewness. Okay? You won't really see this one a lot in this chapter. We'll see it later on. Most of the time, it's going to be either one or two we're going to use. But those are the three options we have to check that condition. Okay? Those are the three options that we have. So when they talk about sample size being big enough with means, they're talking about central limit theorem. You're going to see that. Because I know students always, so like in past group tests, when I hear students talking, they'll be like, oh, central limit theorem, what is that? It's because it's one of those things that's, gets lost in the shuffle. It's when sample size is large enough, around 30. So I would say you're pretty safe less than or equal to 30. If n is less than or equal to 30, sample size, you can use the central limit theorem as an explanation for condition 3. Okay? Most of the time, it'll either be 1 or 2. Like I said, rarely is the case where doesn't tell me population is normally distributed, sample size is too small. What do I do? Well, then I have to check to see if there's any outliers or strong skewness. Okay? Mainly for outliers. Okay? And then these are the 3 options here. I listed the 3 options here. I put them on the board too, but these are the 3 options. If the population distribution is normal, it's stated as normal. It's always going to be normal, no matter if you take how big your sample is. Number 2, it's not normal, or they didn't state it, but my sample size is big enough, greater than or equal to 30. I can use central limit theorem. Okay? If the sample size is small and they haven't mentioned anything about population shape, then I would have to check things like skewness or outliers. Okay? Okay. And then a little more into the central limit theorem. You can see that this population was not normal. It's what we call uniform. Right? There's no curves to it. Everything's the same. Everything's the same height. Well, if I take a sample of 2, that's what happens. And if I take a sample of 25, that's what happens. Variability goes down, right? It turns into one of these guys, which is what I want, right? This guy, skew to the right. But if I take a sample size big enough, variability goes down. Okay? This guy here is symmetric, but it's not the symmetric that I want. So if I take a sample size of 2, if I take a sample size of 25, as that sample size gets bigger, it's the picture that I want. Okay? That's how the central limit theorem works. Okay? Okay, so went through that kind of fast because a lot of it repeats. A lot of it repeats from last section. Okay, so now let's get to some problems here. We still have our steps, right? We still have our steps. The only one we don't have to do all of the time is number 3, unless we're asked to. Unless we're asked to, right? Same like last. Unless asked. 1, 2, 4, and 5 for every problem. Number 3, if we're asked about the distribution, which sometimes you will be, center shape spread, then you have to do that one. But okay. Okay, so example number 2. Was there an example? Yeah, we redid. Okay, so the heights of young women follow a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5. Okay, inches. First thing we do is label. Label everything first. Well, luckily they've already labeled some stuff for us. So I'm just going to highlight it. Okay. Okay, so, oh, and also this. So it says the heights of young women. Doesn't say where the young women are from, United States, Europe, doesn't say where, and it doesn't say how old, like what constitutes a young woman. So they're really vague about that. But the heights of young women follow a normal distribution. So the population is normally distributed. That's what that means. Population is normally distributed. If I were to find the average of all young women, the average would be 64.5. And the standard deviation would be 2.5 inches. Okay, those come from the population. Those come from the population. Because it says it and because of the symbols they use. They don't use X bar. Right? Okay, so find the probability that a randomly selected woman is taller than 66.5. Okay, so first thing we got to do is state the parameter. First thing, define the parameter. Mu equals. This one's going to start true mean. We have a number for that, 64.5. In words, what does that number refer to? The true mean or the true average what? What does 64.5 refer to? Of all young women, yeah. The true mean height of all young women. 1 point. Check necessary conditions. It's kind of a trick question. When do we have to check conditions? When do I have to do these 3 conditions that we did last week? When do I have to do? When did I say? What was the reason behind doing conditions? Checking them. No. Yeah, but when do we have to do that? That involves this stuff, but why did I say we had to do these at all? When what? So yeah, that's what so you guys are talking about each individual condition. I'm talking about the bigger picture. I'm talking like a bigger picture. Why did we have to do any of these at all? What was the reason we had to do any of these at all? There you go. Exactly. That's okay. When using a sample to infer about a population, that's when we need to use these. When the data I get comes from a sample of 2, 10, 15, a million, whatever the sample is, that's when I have to do this. Okay? So go back to the question we're just looking at. A, what's the sample size? There is no sample size. I'm just randomly plucking one young woman out of all of them. There is no sample size. This doesn't involve a sample. This involves straight from the population. So I don't have to do these. This question, I don't have to do these. It's not necessary. Okay? I wouldn't even be able to do it because when it talks about sample size, what number would I use? I wouldn't be able to use a number, right? So we don't have to use conditions or assumptions for this problem. The next problem we will look at B, because it says that's where we get a sample. So the next one we will, but this one we don't. Okay? Because there was no sample size. There was no sample. Okay? So we could skip that step. We don't need to do that. If it's a 4-point question, that's an easy point. You get it because you didn't have to do it. So it's just kind of a gimme point. So we go to the next step. The next step is use the normal model to answer the question. Okay, so let me draw a picture. The true center, it said, was 64.5. The question says taller than 66.5. 66.5. That's what I need to find. Okay, what's the probability that of all the women, all of the young women, I put every single young woman's hat in a name in a hat. millions, talking about billions probably, right? I reach in there, grab one name. What's the probability that that one young woman has a height greater than 66.5? That's what the question's asking. Okay, so I got to use a z-score. 66.5 minus 64.5 divided by 2.5. So let's see, on top I get 2 divided by 2.5. 0.8? Perfect, 0.8. So then I go to my charts, right? That's the z-score. So you go to your table. 0.80, 0.80, and I get this number right here. 7.7881. Is that number represent the shaded or the non-shaded side? The non-shaded, good. Anything from the table is shaded to the left. That's not the side I want. So I go 1 minus 0.7881, and you get 0.2119. Okay, last step. Tell what that number means. Well, the probability that a randomly selected woman, young woman, is taller than 66.5 inches is the probability that the randomly selected woman is taller than 66.5 inches is 0.2119. A little over a 20% chance that they're taller than 66.5. 66.5 is around 5'6", 5'6.5". Okay, the average woman, it says, the average young woman is about 5'4.5", between 5'4" and 5'5". Okay. So question B, I get this question a lot. Question B, what's the difference? It's the same question, isn't it? Aren't we trying to find the probability the bigger than 66.5? But this time, we have a sample of 10 young women. It comes from a sample of 10. So they had a hat, big hat, with the names of every young woman. Instead of just picking one, they're picking 10 and then finding the average of that. What's the probability that the average of those 10 that I picked is taller than 66.5? Okay, that's the difference. We're not talking about 1, we're talking about 10 now. Okay, so step 1, parameter, true, mean. Same as before, it's the same background, same as before. True mean height of young women, of all young women, or what did I put before? Of all young women, yes. Okay, 1 point. Next point, conditions, assumptions. I have to do them here because it comes from a sample of 10 now. Now I have a sample size. I have a sample size of 10. Okay, so now I have to do those conditions, assumptions. They're necessary for this one. Okay, so let me do them over here. So we say connect condition, check. Condition number 1, SRS. Does the sample of 10, is it an SRS? Yeah, it says it right there, an SRS. So we say stated. Okay. 10% condition. N less than or equal to 10% of big N. Well, N is 10. Again, I don't have a number for big N. I don't. But what would I put there? All young women, yeah. And I can pretty much guarantee you that's going to be true. All young women. I think there's more than 100 young women in the world. Pretty sure. 3 is shape approximately normal. We have 3 options. 3 options to put there. Let's go back to those 3 right here. You're gonna pick one of the 3. One of the 3. Doesn't have to be all of them, could just be one. As long as one is okay, we're good. If the population is stated as normal, then I'm good. If the population is not stated as normal, but the sample size is big enough, 30 or more, then I'm okay with using the central limit theorem. Neither of those work, and I have to check for outliers or skewness. So let's go through it. In the question, does it say population is normally distributed? It does, right? It did. Absolutely, it did. It says the heights of young women follows normal distribution. Boom, we're done. It's stated. Population stated as normal. So you say population is stated as normal. Make sure to capitalize normal, because normal refers to a person, not like normal average. It's not that. The person who came up with normal distributions is actually, their last name is Normal. So that's why it's always capitalized. I don't know. Honestly, I don't know. But I mean, it's just always capitalize normal. Anytime you refer to normal distribution, yeah, capitalize it. I know it's weird that, but it is. It's true. Normal. That's why it's called normal distribution, because the person who discovered it or came up with it, or their last name was Normal. Okay. Okay, that's step 2. Step 3. Let's draw a picture. The true center is still 64.5. I'm still trying to see if exceeds 66.5. So the picture is going to look very similar to the last picture that I did for A. So I get 66.5 minus 64.5 over, what's the standard deviation? Yeah, I didn't know it, right? I'll get a lot of students that try to put 2.5 in there. That's from the population, right? I have to find the standard deviation of the sample. That's this guy right here. That's this guy right here. The original standard deviation divided by the square root of n. Okay. So the standard deviation is 2.5 divided by the square root of 10. 0.791. Okay, around 0.791. That number is going to go down here. Okay. We still get 2 on top, but the number on bottom is not 2.5 anymore. It's lower. So that means the z-score is going to be higher. And what's the z-score? 2.53. Bigger z-score. Bigger z-score means bigger percent, bigger decimal. 2.53. Yeah, it's pretty much 1, right? 0.9943. Again, that refers to the blank side. It does not refer to the shaded side. So 1 minus that, we get 0.0057. 0.0057, that's like half of 1%. So the probability on A was 0.2119. The probability with B went down dramatically. Why? Why did the answer get smaller, go from about 21% to like less than 1%? 21%, if there's a 21% chance of something happening, it could happen. Less than 1% means it's not going to happen. So what's the difference? What was the only difference between the two? Well, obviously, but what's the difference between the two problems? Exactly. The bigger your sample is, the more likely it's going to do what the center says it should do, right? The first one wasn't a sample, it was 1. I picked 1 girl. The variability there is high. Anything could happen with that 1 person. But if I were to pick 10 and add and find their average, the bigger the sample size, the more it's going to want to be closer to the center, right? The bigger your sample size, the more it's going to want to do what the center tells it to do. The center is 64.5. So the bigger my sample size, the more it's going to want to be 64.5. The average is going to want to be, took a sample size of 20, 30, 50, 100. It's going to want to be the center, closer to the center. It's not going to want to be farther away, right? So that's why the probability went down. If I were to take a sample size of 100, change 10, make it 100, right? That probability would go even down further, right? Because the bigger the sample, the more it's going to want to be in the center, right? The more it's going to want to be in the center. All right, so last thing, write in a sentence, and we're done for today. Let's see. The probability the mean height of the SRS of 10 is greater than 66.5 is virtually zero. The probability that I reach in the bag, grab out 10 girls, young girls' names, found their average. The probability that the average of those 10 girls is bigger than 66.5 is less than 1%. Okay? The bigger the sample, the more likely it's going to do what it should do, which is hang around 64.5. Okay? This one's a little bit, 66.5 is a little bit farther from 64.5. So the bigger the sample, the first one didn't come from a sample. It was just one girl. I picked one girl's name. There's high variability. High variability in doing one thing. If I go to a casino and I go today, just today, anything could happen. But if I go for 100 days straight, chances are I'm going to lose. I'm going to lose a lot of money. Okay? Yeah, I mean, you have, because variability is very small. Anything can happen at once. But if you do it a lot, you're going to lose. You're going to lose. Okay?